Thank you, Matt. It's always a privilege to speak at Demuxed, so I appreciate that. And I appreciate everyone waiting to the end of the day for this talk. So you're probably wondering what you're waiting for, right? What is this guy talking about today? So a couple of disclaimers, or spoilers, as I might even say. The monkeys, for the animal lovers, are just abstract constructs. There's no actual monkeys. And in fact, there is communication, but it's not at all discrete. I put monkeys in because it's standards, it can get boring, and you either go with puppies or monkeys, and I went with monkeys pretty heavily in this talk. So I'm talking about common media client data. It's a standard. We'll probably never say that again, it's too long. We refer to it by its acronym of CMCD. It's already popped up in several presentations today, but I'm going to go into it with some depth to explain what it is and explain some really interesting use cases and things that I've found super interesting about it. A spec must solve a problem. So what problem are we solving? We're solving a problem between the worlds of players and the world of content delivery. There's been many sessions today. Every one of them has mentioned some type of distribution, some type of player. And these are quite distinct and decoupled worlds in many cases. So we look at a playback session. It lasts for an hour. It's got 2 rebuffering events from one player. On the CDN side, you're seeing a bunch of logs flying by. At Akamai, we see 66 million or so logs per second. We don't know which are attached to which player in which session, and we have no idea if any rebuffering occurred. So we have 2 data sets that are quite explicit, but they're not joined. And CDNs are somewhat blind to the characteristics of each request. So I show you a URL that you might see in a log line. There's a GET request, and I challenge you to answer these questions on this. Is this a 2-second or a 6-second media segment? That matters, because how long do I have to return this thing? I can't tell you that. Is it HLS or dash? Both use CMAF, I can't tell you there. Is it player in startup or steady state? You may ask, why do I care? But I'll get into it later. There's some very strong reasons to care about this. What's the bitrate of the object? Who knows? Is it an audio segment or is it 8K video segment? Is it video or audio? Is it live or VOD? I can't tell at the edge server, it's stateless. Is the player healthy or rebuffering? And importantly for a CDN, if I deliver this in 2 seconds, am I doing a great job or a terrible job? Right? If it's an 8-second segment, it's a great job. If it's a 2-second segment, it's not good to deliver it in 2 seconds. So we are pretty blind on the CDN. And from the player side, they often say, why doesn't the CDN know there's poor performance in Chicago on Tuesday night in this ISP? And unless our servers are pegged at 100% for some reason we can see, we have no idea that the delivery is actually slow. We have people wanting to tie their QoE logs, and there's many providers of those to their CDN logs. How do I tie them together? What's the common join? How do I consistently tell all CDNs to prefetch my content? Prefetching is pulling it to the edge ahead of a request, but is there a single way to do that that's understood by all players and all CDNs? And your CDN world is always in hits. We had so many hits. That's because we can't construct sessions out of those hits, and you don't know how many videos are being played. So there's a need for players and CDNs, or whatever your distribution mechanism is. It doesn't have to be a CDN. It can be straight out of your EC2 instance. But we want to exchange mutually beneficial information with one another. And luckily, and here are abstract monkeys making requests, we already have very clear and well-established mechanisms for doing that. We have query orgs and we have custom headers. So that's our communication structure. It's not going to be more complex than that. And a group got together and did the work. You've heard their name before, CTA Wave project. Wave's a bit obscure, but CTA is the group that gave you HDMI standards, 608, 708 captions, and now they're giving you a bunch of quite useful and practical OTT-related standards. So a bunch of us worked together on this. It came out in September 2020. It's free, it's open source. You're welcome to download it and use it. There's no royalties around it. So CMCD then is a defined set of structured key value pairs that communicate mutually beneficial related information from a CDN down to a player, from a player down to a CDN via either one of custom headers, a query org, or a JSON object. One of those, not all of those. And we call it common because it's the same data structure that can be used by all players and understood by all CDNs. It's not custom or specific to any one CDN or any one player. It's available for free. There's a spec at a tiny URL. So here in a summary, this is all the keys that are sent. We didn't want to reinvent QoE metrics. There's companies, Mark's nice people at work, Conviva, that do a great job at this. We wanted to distill down some of the most important information that the player can send. And the beauty here is it's not beaconing off to a third party. It's piggybacking this data on the request that's already making to play the content. And I'm not going to list them all. You can read them. Credit to the group for getting an international standard where BS is actually one of the most important parameters that we pass. We laugh about that one. What do these look like crossing the wire? Well, what you might expect. Here they look like as headers. Pretty readable, human readable, in fact. As a query arg, it's just a URL encoded version of semicolon concatenated header data, and JSON looks like JSON. I should point out that we shard the headers across 4 different headers. And that's so that we don't blow up HPAC and QPAC dictionaries. If we put everything in one header, it would change all the time. There'd be a new entry in the dictionary. So we shard it based on the expected entropy, the change rate of the information that's inside the header. So some use cases. What can I do with this that's practical and useful? So the first example, and the one that big providers are going with directly, is prefetching non-monotonically increasing segment numbers. So I don't know if you can see at the back of the room, but these are actual segment names from a very large global OTT provider that are very difficult to guess on the CDN. We have to write very complex edge-based code or brittle regexes to try to guess this. But with CMCD, it can simply hint to us what the next object in the request is. So it requests one segment, it hints that, we go prefetch it, it's there when the player makes a request, and we get a faster, effective throughput for that segment, delivering it to the player. And this is a consistent nomenclature that all players can use to activate prefetching on a CDN. Number 2, multi-CDN client steering. So this actually comes from Paramount, and this was a talk given at Mile High Video. They're using CMCD data, which reports buffer length and bitrate and whether it's had a buffer starvation event, collecting that data from real players in real time and using it to steer new players joining into the better performing CDN. And this is the bitrate over the top bitrate, which are both CMCD parameters, being tracked here over time and allowing you to differentiate the performance of 2 different CDNs. Number 3, session identification through Apple Private Relay. So Apple Private Relay is rolled out. It's basically two proxies with a mask tunnel between them, but it hides the true IP address. So for a lot of you have systems that take IP or user agent plus IP as a unique tuple and try to identify sessions based on that. That is going to break, especially through Apple's Private Relay and other private relay and privacy proxy layers that are going to come out. But by adding session ID to CMCD, you can have a robust identifier that makes its way. And you're not giving up identity of the user. Session ID in CMCD is randomly generated every single time a user plays a piece of video. It's just there to tie the requests together, and it's never, ever repeated. It's a GUID. Use case number 4, get real-time views into player health. This is super interesting. So because CMCD is giving us a session, we can break it out of the millions of other sessions that are concurrently playing on the CDN and look at the actual buffer length over time. So here I have the same video being played by 2 different players. The top player is Shaka, and the bottom player is HLSJS. And we look at this and you go, okay, this looks normal to me, but then you see a zigzag pattern, which is pretty typical of loading, but each dot there represents a segment. So why is the sawtooth pattern on HLSJS comprised of multiple segments? What's going on every 12th segment in HLSJS? This was super interesting, so I analyzed it in a little more detail. So this is a zoomed-in view onto that player, and here's what's happening. The player loads a 6-second segment, and it's delivered in 600 milliseconds. That's because you got this is a well-connected client. The CDN is delivering it 10 times faster. What happens then is it waits 6 seconds before loading, and this is actually what the Apple spec suggests. You wait the duration before loading the next segment. But the trouble is we've had 6,600 milliseconds of wall clock time elapsed, and we've loaded 6,000 milliseconds of media time. So what happens? The player buffer declines by 600 milliseconds. And it keeps declining every step until it reaches a point down here, the 20-second mark, where it just says, oh no, I'm too low, I'm below my target buffer. It quickly loads more data, pull itself up to a higher level, and then this process begins again. So we have a long-term period oscillation, in this case about 60 seconds. And what's interesting is the slope of this line is proportional to the speed of your connection. The shallower the line, the faster you're connected. Now, there's a super interesting anecdote. I actually showed this slide and this data yesterday at FOMS conference here in San Francisco. And Rob Walsh, who's the maintainer for HLS.js, looked at it. And to his credit, he looked at this, he goes, I showed it to him at 3:30 p.m. By 5:11, he filed a PR to address this. So I just want to say that's how you maintain a project. And I would say half this room use HLS.js for commercial gain, and you don't pay a cent for it. And I don't know if you've ever stopped to think of who on a Tuesday afternoon is working to make this product better. So it's not an anonymous person, it's Rob. He's at the conference. So buy him a beer, and if not that, at least say thank you for what he's done. And also to people like Jean-Baptiste for FFmpeg. These are not normal people, they're giants in our industry, and we need to respect them for who they are. So, use case number 5. Build yourself a QoE monitoring. This is the fun part. So this was Sumo Logic. You can use Datadog, Splunk, Grafana. You've got this data coming in. You've got a mixture of all your CDN logs, which is giving you visibility into location, AS, network identification, geolocation. And then you get all your player, well, not all your player data, but you get a subset of your player data that lets you monitor your player health in real time. And it's very interesting. I won't go into more details about this, and I think we can imagine what it looks like. Number 6, start digging into this data and looking for interesting things. So I did just that. I did a survey. It was 2 minutes of a major USA OTT provider. That was almost 19 million requests in that 2 minutes and 181,000 different sessions. And here's some of the things I found. So this, it's cut off on the side. This is the CMCD measured median throughput. So what do you think in the United States the median throughput was for this data set? Turns out, and I've seen this in some, reflected I think in some of Mark's data earlier on, 38 megabits per second. So that's kind of interesting. That's what we are in the United States now for median-based throughput. 5th percentile down to 1.7. So that's probably where a lot of the problems in delivery are occurring, or some of them. The highest bitrate offered, 6.8 megabits per second. So notice we're in a world where the median throughput is 5 times the highest bitrate that's being offered. So it's not that you can't deliver higher bitrates to users, it's the economics of delivering it are not justified yet. So that's interesting. So then I plotted this chart. So on the vertical axis is CMCD measured throughput. So measured throughput is the player's view of the throughput it's getting. And it's very interesting to see this. On the bottom is all the ISPs identified just alphabetically, A to Z. And I scaled each one by the number of users in it. So what we can see, firstly, that there's a variance in throughput. It very much matters. Your streaming experience matters by who you choose to provide your last mile. And we'll see very quickly, even in the city you're in, it matters quite dramatically. We notice that generally the bigger ISPs tend to have better performance. There are some outliers up here, but they're a small number of users. But these are the big guys, and they're all, this median level is around about the 38 megabit per second mark. There's some large ones down here that are not performing well, and I'm not going to name names, but they're down there. So then I looked at, does higher throughput mean higher average? We take it for granted, right? If I have better throughput, do I actually get a better bitrate on my ABR player? Does ABR work? So here on the horizontal axis is the average measured throughput. The vertical axis, the encoded bitrate that the player was playing. That's another CMD parameter reported. And we can see here a clear trend. And it's curving down because there's, again, we have a maximum bitrate that is being delivered in the sample that I measured. We must be very careful about constraining the scope. I took a 2-minute sample from one provider, so don't make super big generalizations about this. But again, an increasing trend, as my throughput increases, so does my average bitrate go up. And again, it's scaled by the size of the ISP. So the bigger ISPs generally performing a little better, and we got some problem children down at the bottom here. What about within a city? So I took the Chicago DMA. There were 760 different ISPs identified. Now, they're not a full ISP, right? It's the AS identified serving the content. Some of those are school systems or mobile buses or things. Then I took the top 11 or 12 by volume served, and I plotted them out. And we see again, a clear variation in ISPs for the same content on this provider. And I think Matt was asking earlier about satellites. So here we see a clear difference between SpaceX with low Earth orbit satellites and Viasat with geostationary. And they both showed up. They were both coming down to users within the Chicago DMA. So think carefully about who you choose for internet access. How often do OTT sessions switch bit rates? So we have a lot of ABR decisions, right? Ali's built a career out of analyzing ABR. But do players, are they switching all the time? Is it just crazy switching out there? So this was data gathered by Mark's COP team, or by code that these guys wrote. And it's super interesting to me that the median is that most sessions never switch. So you can see down at the bottom, 0 for the median. And in fact, the upper 10% contain all the switches, and of that, 1% contain 2/3 of all switches. So there's a very small percentage of players that are switching a lot to cope with poor bandwidth conditions, but the vast majority, 90 percentile, are not switching at all for this OTT provider in the time that I sampled it. It's not generally applicable, but I think it's quite insightful that switching is not occurring. Most players start at the highest bitrate and stay there. Now, which companies are using CMC? Is this a figment of my imagination? But no. So here's brand names and some quotes. Now, these are just companies who actually I've worked with and who gave me permission to use their logo, which is also, or gave me a quote, so thank you. There's a lot more people using it. I've already had discussions in the room today, and it's come up several times. So if you're dipping your foot into it, don't think that you're the first. You are not the first swimmer in this swimming pool. And speak to one of these companies about their experience. So you can add CMC support to any player where you can decorate the outbound requests, right? Because those properties, buffer length, has it rebuffered, those are all commonly available properties. You can read that data and then add either the query args or the headers yourself. But the idea with a common media data is that you do the work once in the player and then everyone can benefit from it. So the work has been done in a number of well-supported players. Dash.js was the first, credit to them. HLS.js, Shaka, that was done by Paramount, so thank you for them. Roku player, who I'm going to point out, are widely distributed. And Ali just told me RDK at Comcast is now supporting it. So this list will grow. There's an open ticket for Exaplayer. People already have support. And I'm recruiting someone to do the integration work there. So speak to me after that. The king of the CMCD players by request is Roku. And I want to give them credit for that. Since version 11, they've been supporting CMCD by default. And since 11.5, which is the new version coming out, they're going to support the advanced fields around prefetching. So if you're an OTT vendor that's using Roku, and Roku are driving 31% of all minutes viewed in North America. So there's a tremendous amount of CMCD data already available, and it's there for the taking and there for the analyzing if you own the logs and you are the content distributor. So by all means, if you're using Roku today, check into it. So now you ask the question, well, what if I don't have player support? Am I done? I can't do anything with CMCD. I'm out of this picture. And this is not actually true. So I want to introduce, I forgot to add the sound effect. This is Anders, and he had a bright idea. He's like, you know what? Media playback is sequential. There's a hierarchy. I load a playlist, I load a variant playlist, I load media segments. We can take advantage of that, and we can actually inject CMCC data. So let me show you how that works. And we're going to inject it by means of a proxy. So for that, we're going to build a test bed. HLS.js player without CMCD enabled. Remember, it's got a simple property. You can turn it on, but we're using it in its native state. And I'm also going to use Safari playing an M308 directly, because AV Player doesn't have native integration for CMCD yet. So we run that through an edge worker. This is just our implementation of JavaScript at the edge. It's going to function as the smart proxy. Then we run it through a CDN. The CDN gives its real-time logs out to an instance running on the node, which is running Grafana, and we're able to analyze the data. So relatively simple test bed. You can build it in many different ways. Here's what we can do with the playlist processing, which is kind of interesting. So here's the primary playlist. I'm doing HLS example. This works for Dash as well. It comes in. First of all, I can see there's no session ID. So I can add one, right? I know that this is the very first request for this, so I synthesize a session ID. It would normally be longer than that. I just made it short so it fits in to my picture. Then I know the stream format is HLS, so I can decorate that. I know the object type is a manifest, because this is my primary manifest. And I know that the bit rate of this variant is 1,054 kilobits per second. So I add that in there. And I can also add that the top bitrate is 6,064 because I can parse the playlist and figure it out. So that's already useful information that I get my proxy here. So I fill it out for the rest of the fields, and then I URL encode it. And that's what my proxy would do to decorate this with CMCD info. The variant is also similar, but I can actually add some even richer information. So I inherit some of the session ID and the other top bitrate information coming down from my master, but now I can add that the stream type is VOD versus live. I know the object type in this case is an init segment, and it's also startup. SU is a parameter that says this object being requested is important. It's involved in the startup phase of video, and that therefore the CDN might want to do something special for it. And for my video segment, it's very similar. I decorate it with the stream type as VOD, the object type as video. It's also startup, and now I can add on the explicit duration of the segment because I simply read it from my playlist. So I do that for the rest of my segments, and I URL encode them, and off my proxy goes. So on the server side, we can gather information quite simply. The number of sessions, I simply sum up the number of unique session IDs. The estimated player buffer length, because we don't actually know the buffer length of the player, but we can guess it by summing the media duration that's been sent minus the delivery duration. So if I'm a server and I send you 10 seconds of media data in 2 seconds, you've probably got an 8-second buffer. And at least it's an approximation to it. And then for video start time, you can guess it by just saying how long did it take for the player to request the third segment. It's a rough approximation to video start time. Not precise, but it scales with true video start time. So you put all of that together. Here's a screenshot on the right-hand side. I got 4 players, HLSJS, playing Big Buck Bunny. And now I'm going to open up Safari and play my M3U8 directly in it. And the cool thing now is that we can invoke AV Player, but we can still see all the requests that are being made. So I'll launch M3U8, and then I'll go and look at the primary playlist. And we can see there that, in fact, our proxy has added in this information for us. So what I just described is being added. That was not there in the original playlist. And then I can go look at one of the variant playlists. And again, we see that there's more information. It's URL encoded, so it's a little hard to see in real time. That's the information down there. And then you look at one of the media segments. Apparently, I can't right select, but I eventually left select, and off we go. So that's the data on the player side, and then we can hop over and just take a quick look at the Grafana, which was showing us our proof of concept origin. So I've got up here the session count. That's all my new session establishment. I got segment fetching throughput. I've got the playback bitrate of my individual sessions. You wouldn't actually track thousands of sessions. We're just doing it as to show that you can uniquely select them. I'd show aggregates, our segment buffer, status codes, and also the log delay, because I know I've got a timestamp in my log line, and I know when I'm processing it, so I can see how fresh this data is. So this is just a proof of concept of how you, with these simple proxies, and we use proxies for ad insertion. So if you're already modifying a playlist to do ad insertion or dash manifest, you could add CMCD data at that point. Now, there's some curious opportunities to be found in steady state, and this is an area I find super interesting. Let me explain what I mean by steady state. So when I'm a media player and I start requesting things, my buffer is vertical, time is horizontal. I load segments as fast as I can. That's the blue stuff. And the dashed line is my buffer, it grows. And what happens then, I reach a target buffer level, which is this one. My buffer declines, and then I load a media segment. My buffer declines, and I load a media segment. I load a 6-second segment every 6 seconds, but it only takes 1 second to come to me. So what's interesting is this yellow space or white space, we might prefer to think about it, is free space, right? And what can I do with this free space? Well, the area to the left is the startup phase, and here we have the steady state phase. And the steady state is shown by the spacing out of the requests. A lot more gap between the requests. Here they're close, here they space out. Typically, as a CDN, we have no idea what state the player's in. But with CMCD, it can tell us. It explicitly flags, I'm in startup or I'm not in startup. So what we could do is I could actually insert some time I could delay responding to that segment. And what it's doing, it's pushing my buffer curve down, but it hasn't pushed it to the point at which the buffer level will cause a switch down. So I haven't affected QoE on the player, but now I've got a gap And this gap is interesting. So I started thinking, let me build a test bed because I want to investigate this. So take a CDN. You can test anything in media with Node.js and something to do with Big Buck Bunny. So this is Dash.js player. But then I need an objective measurement of quality. What does this look like? I don't want to affect the quality of the player. And I have to say that I tried Mux, and it was super easy to use. It took me about 5 minutes to hook up Dash.js and be getting metrics in about quality that I could trust. So I used that, and here's a video of it working. There goes the proxy I set up. So this is a player. And I set my proxy, the player's given a 30-second target, and I set the proxy to start injecting arbitrary delays before returning segments after 25 seconds of buffer. And why 25? It was 30 seconds minus 1 segment duration plus a second just to give a little breather gap. So ideally, when the player is in steady state, it should be adding delay. And down here, you can see it's adding 2 seconds of delay in each segment that is returning. And we're playing 4K video here, 12 megabits per second, and we haven't switched out of that. So that was interesting. So I just picked 2 seconds, but then I'm interested, how much can I inject? So I did a series of tests. So here we see the Mux QoE metrics that Mux is collecting from the player automatically. And this 0 milliseconds means I'm injecting 0 delay into this. And they were good. I am well connected. I was playing nice video. This is probably as good as most playback gets. But then I started adding more and more amounts of delay, 1 second, 2 second, 3 second, 3.5. And these are 4-second segments, and I've set a 30-second buffer on an unthrottled connection. And what's interesting is our viewer experience does not change at all. It's very highly rated. Startup time does not change, or barely. Sorry, that's the startup time score. That's the actual startup time. Slight increase here, 3.5. But 3.5, that's a lot of delay for a 4-second segment. And I do start to see a degradation finally on weighted average bitrate because it was switching down from the 4K. So I thought, well, those are cool results. I can inject a lot of white space here and not affect QoE, but maybe it's because I'm well connected. And you must always, when you're doing this, we test it from offices or home that are well connected. So I repeated this with I lowered the buffer from 30 seconds to 12 seconds, and I throttled Chrome to 5 megabits per second. And I repeated the test. So now our number dropped slightly, all right? It took slightly longer to start up. We got a slightly lower experience here, but still decent. Repeated it, injecting the same amount of time. Again, overall viewer experience, very nice. Startup time starting very consistent. Weighted average bitrate starting to decline. You might say, how come the viewer experience didn't go down when the weighted average bitrate went down? That's because I was looking at it in a small window, and my video was bigger than it needed to be to start with, so the visual impact was not impacted by it switching down. Anyhow, this is really interesting information. We can delay a response, and I'm going to get into what we could do with that. So you're curious then, how much can I increase time to first byte without affecting a player's QoE? So there's a number of properties that I can determine the max delay, and in fact, the max delay is given by this formula. Now, that's the wrong formula. That looks like one of Yuri's formulas, actually. Here comes Yuri. Yuri's coming out. You may not know Yuri, but he's famous for calc. He's going to take his formula back. It's clearly not my formula. And let me bring out my formula. So my formula is simple. Now, it's simpler, but it's non-linear. So let's look at what it's like if we plot it out. So on the vertical axis, we've got delay in milliseconds. Horizontal axis is the throughput between the client and the server. So I notice a number of things. Like, there's a point at which, if I don't have enough throughput, I can't add any delay because I'm at the boundary of switching down. And conversely, it's asymptotic at the top because no matter if I have infinite bandwidth, I'm still going to hit my switch point if I add too much delay. So there's a natural point. And then we get the interesting data. So 20 megabits per second, I can theoretically add 2.5-second delay for a 1 megabit per second 4-second segment, and at 700 milliseconds delay for a 9 megabit per second segment. So the higher the bit rate of the object, the less delay I can add. So that's cool. I've got a formula. Can I build a smart delay engine now? Can I build a server that extracts as much delay as possible while retrieving media data without affecting player QoE 1 bit? So how would I do that on the server? Well, I need to implement this formula, and this is a talk on CMCD, so magically, I get all these properties from CMCD. I get the duration, I get the bit rate, I get the measured throughput, and I can guess a safety ratio or factor of 1.25 or 1.5. And explicitly, we extend CMCD to send that information. So given that, and I will spare you the whole proxy. Here I have side-by-side 2 players. So this one is playing in a 5 megabit per second throttled condition with a 30-second target buffer. And I've set the proxy to start adding delay at the 25-second mark because I don't want to affect startup. I want to be in steady state. And our buffer is 18 seconds here. This proxy has the smart engine. And as we get to about 25 seconds, it will start injecting as much delay as it can. And we notice both players are 2.5 megabits per second, 576p, and they're staying there. They're not switching up or down. That's the best they can do with a 5 megabit per second throughput. But in almost 40 seconds of playback, I've injected 20 seconds of delay across audio and video, 10 seconds for each of them. That's quite a lot. So why is it useful, you say? It's useful because we can start doing things. There's a lot of pressure on CDNs to deliver everything quickly, right? And that's true. At video startup, I have to deliver everything quickly. But I clearly don't need to deliver all my media segments quickly when they're at steady state. So maybe we could cache only the objects that are really important, and we could free up a lot of cache space by not caching objects where I can happily take 2 seconds to retrieve them from either a parent or, worst case, from an origin. So that's an interesting area of research. We can also optimize prefetching. Do I need to prefetch something if a second's delay in returning it is not going to hurt QoE? Maybe not. And again, with the ability to tell where the player is in its playback state, I can start experimenting with that. I can also serve content from further away. Doesn't have to be the edge. The edge is expensive real estate. Maybe I can serve it from a location that's cheaper, or I can serve it from a place that has a lower carbon footprint. And that's starting to become important because sources of green energy and lower carbon are very rare in the hosting space. We buy up all we can, but they're usually further away from you than an edge server is. And then we can also throttle, and this is an interesting solution. I don't have to delay my response, I can throttle it. Why do I care about that? Here's an animation. So a bunch of players all requesting segments. If I'm the yellow one and I measure my throughput, I've got the whole channel. It's going to be very quick, so I switch up. But then just caused by the cadence, when I measure it next time, I'm competing with 3 other players. I don't have the bitrate I had, and I risk rebuffering. And this is what happens when CDNs are very good. Remember that 38 megabits per second was 5 times faster than the encoded bitrate? So we have very small and narrow delivery windows, and this problem is well investigated in academia. What we can do, instead of delaying, is throttle the delivery, make those segment deliveries last longer, so that when players estimate throughput, they get the same answer every time, and there's less thrash on their ABR. So what's next for CMCD? Oh, that's a typo, I just realized. That's the next spec I'm working on. But this is CMCD v2. We're probably going to kick off work in the next 6 months. There's a GitHub issue here where you can go file things you want us to add. 2 things we're going to add that I'm personally interested in, assuming people agree with it. One is an explicit marker for video start time, so we don't have to guess. And then also add a target buffer, so we can normalize your buffer length by your target and collect data from a whole cohort of players. And I like to thank people. I'm just the lucky guy who gets to come on stage and talk about this, but a lot of people have done a lot of work around CMCD, and I list some of their names here, but not all of them. So I thank these people personally for their commitment and involvement. And at this point, the Code Monkey says, thank you very much for your time.